Hi everyone, my name is Prakal Binzade, mining consultant here at the MineOpt. Over this series, we are breaking down the strategic mine planning step by step. Today, we are kicking off with the real gold deposit block module inside the MineOpt. In the next few minutes, you will see how I bring the Surpac CSV straight into the MineOpt, explore it in the full 3D view, and flip instantly between the ore and the waste. Pull out the zones based on the report and the sections, and wrap up with the quick pit shell showing. And if you are ever wonder how to go from the raw block data to the optimized shell in the one workshop, in the one software, it will body you. Alright, let's jump into the MineOpt. Alright, let's start by importing the block module. This is the CSV file exported from the Surpac. And as you can see, MineOpt picks up the XYZ coordinates and the size of the block and the grid, gold grid automatically. Just quick check to make sure all the blocks are in the same size. Looks great. So we are ready to go on the 3D canvas. Now we are in the 3D canvas inside the top. I will just rotate it for you. This helps you to get a quick sense of the block layout and the orientation. This is really helpful for understanding the deposit at its glance. I am here coloring the ore by the blue and the waste by the red. As I adjust the cutoff, you will observe how only the higher grade zones remains valuable. This is the first way to check where the most valuable material sits. Yeah. Now I am switching to the simple ore versus the waste view. And based on the 0.8 grams per ton cutoff, blue blocks are big ore and the red are the waste. In the practice, we do try different cutoffs to see how to impacts the revenue and pitch it like that. Let's pull some basic numbers row. I'm just selecting the none for the waste and the ore. It gives you the report results right by here. MineOpt gives us the nice background actually, tonnage grade and the contained gold even by the rock type. This kind of report is greater for the earlier stage project analysis. Now I already run the LD pit shells. The slope angle is the 50 degree and I have based on the gold price, sales price we can say. So I am switching it directly into the pit shells that is generated from already in the MineOpt. And just a quick set, and we did the first view of the optimized pit dock lines. Is the OPT20, the ultimate pit shell, as you can see. Let's cut this section. Here at the 10-200 north, this is the clear view of the internal structures like that. You can just click on it, as you can see. This gives the clear view of the internal structures and the grade variation that all the sections. Always good to cross check with what we earlier saw in Surpac, right? This is actually nice. So that's the full walkthrough from the block module import to the pit shell, done entirely in the MineOpt by the help of exported block module from the Surpac. Now we continue our part of this video that is explained how the different software takes over the block module. See you in that. Thank you.
Hello everyone and welcome to our strategic mine planning series. My name is Prakal Binzade, mining consultant at MineOpt, and in this series we will simplify the complex planning concept. And in this video we will focus on the block modules through to the scheduling using the MineOpt software, for example, and we will get to know about the different kinds of software we use in the mining industry also. So what is block module? In mining, block module is a 3D database of your deposit. Imagine dividing the ore body into the grid of rectangular blocks, each storing the values like ore grade or the rock type. There are two main type of the modules we can say, like the block module for the hard rock deposit and the grid module for the stratified deposit like the coal seam. Each block in the module has the attribute for whether property we want to estimate. For example, in the gold mine block module, each block might holds the data on the gold grade and the density, and the block module lets planner visualize and quantify the ore body, much like the stacking the bricks to the represents the underground geology. Different software tools are used to create these modules. Hard rock mines often use the package like the GeoS, Surpac, and Datamine. For instance, the copper and the gold mine often model their deposit in the Surpac or the Datamine, export those modules for the planning. And the stratified layered deposit like the coal or the potash commonly use software like the Datamine and Minescape and the Minex, mostly common SIM tools. For example, large coal producer in the Australia might use the Minex and the Minescape to module the same thickness and quality. Ultimately, these different tools all produce the block and the grid modules. Hard rock mines produce the block modules and the coal mines produce the grid module, as we discussed earlier. One common format in the Surpac block module, often used saved as the .mdl file. Surpac by GVA is used worldwide now. Think of the copper mine in Chile or the gold mine in the Australia building its block module in the Surpac. The .mdl file contains all the block data like the coordinates, the grades, and the rock codes, and much more in the Surpac's format .mdl. In practice, if you have worked with the Surpac model, you will recognize how the data is in the 3D environment, right? Surpac's block model is defined in the 3D space. We set the minimum and maximum coordinates like in northing and easting and the elevation. Each block represented by its centroid coordinates like the y, x, z. All attributes for that block like the ore grade and the density are stored for there. For example, at the gold mine, you might see each block latitude, longitude, and elevation associated the grams per ton value. Importantly, Surpac allows the variable block size, but most planning we use the fixed block size to simplify the calculation. The model space in the Surpac is defined the extents of your block module. You input the minimum and maximum coordinate like the northing, easting elevation of the region to cover. For example, the copper project in the Mongolia might define the block module from the northing 5,000 to 15,000 and the easting from the 2,000 to 12,000, and the RL would be 1,000 and to the 2,000 meters. Each block centroid define its position actually, and the Surpac stores those centroid coordinates for each block. So your entire module might be a large 3D grade the deposit area, right? Each block has the attributes, fields like the grade, ore type, and density. Surpac supports the several datasets. For example, you can have the character fields like the rock type names and the integers like the rock code and domain IDs, and for the numeric value like the grade and density, or calculated fields, of course. In the practice, you must numeric properties like the gold gram per ton or the copper percentage are stored as floated with enough precision. Importantly, Surpac does not allow truly empty fields. So every block attributes has the value, often a background no data numbers. Imagine a block with the 10 gram per ton gold and the rock code by 5 and density by 2.7. Those are stored as the attribute in the module, right? Surpac has the feature called the super blocking. Hope you know. It collapses adjacent blocks into the single large block if they're all attributes identically. This saves the memory and the speeds up the processing. For example, if you have the 1,000 blocks all within the same ore code and the grade in the zone, Surpac can combine them into the one super block. There are two methods actually. This standard subblocking required the 8 adjacent identical block to merge, and whereas variable subblocking can merge favorite block depending on the size, right? The benefit is they reduce the file size, high storage efficiency percent, but we cost for the optimization softwares like the MineOpt. All blocks must be in the same size. So after exporting, ensure no super blocking remains for the MineOpt. Often we export the block module to the simple text CSV file, we can say Excel file, commonly known. Most software can output a CSV where each row is the block and the column are the attributes. This is called the flat file, and or we can say the ASCII export. You can then open it in the Excel or the script. For example, a mining engineer might export the Surpac model to CSV to quickly filter blocks by grade. Large models can exceed the Excel's row limit, in which case a specialized viewer are needed. But the advantage is the transparency. You can see all your data in the one table. A flat file CSV is easy to understand. The first row are header telling us what each column is. You can edit it in any text editor or the spreadsheet, obviously in the CSV format. This makes the verification simple. You can manually spot check blocks size or the grade. However, remember, for software optimization, especially for the slope calculation, each block must be exactly the same size. If Excel shows two blocks with a different dimension, that could be a problem for the downstream scheduling. Because CSV is a human readable, it's can called be editable block module, right? Engineer often use it for the quick fix or the quality check. For example, you might use the Excel to filter all the blocks of the certain rock type or fix a missing attributes value, right? The slide shows an example open in this Excel as the tip. Always double check your blocks dimensions column is constant, obviously. If not, when you import this into the MineOpt for the scheduling, it may be rejected model. The note on this slide remains for optimization, like the calculating the bit slope. All blocks must be in the same size. Now let's switch over to Whittle, we can say a common strategic planning tool. Whittle uses its own block module format. It takes the block module from the another program like the Surpac to process it. Whittle format, it's coordinate based. It uses the block identifications like the IJK represent the block grade. It's more abstract, like it doesn't store the grades but rather contains the metal, like the ton of the metal, for example, is for the each blocks. Many large open pit projects, that is the copper or the iron ore, use the Whittle to run the optimization. We will cover some key files next. A Whittle block model is saved as the .mod file. This file lists each block by its IJK identification, we can say, and any parcel inside it. Think of IJK as the simple 3D grid coordinates, block rows and the column and height. For each block line, we will list the attributes like the MCAF and the PCAF. Block with the ore are broken into the parcels portions that makes the known ore type and the metal contents. For example, the line like IJK 1936-1 shows the block by 1636 by 1 is sulfide with the 2106 tons and some metals. In practice, plants might look at this copper mines Whittle model, where the block 1025 has the 500 million ton of the ore, right? Whittle also uses the .par parameters file. This file defines the block dimensions, the origin and the model size. For example, line 1 might say each blocks is the 10 into 8 into 10 into 8 meters. Another part gives the model origin rotation and how many blocks in the XYZ, the framework dimensions. The parameters tells the Whittle how to interpret the .mod file. So if your Surpac model has the 100 meter into 100 meter into 10 meter block, your parameter would be reflect that. Always double check this file. Any mismatch will misalign your blocks, right? The Whittle framework origin is the spatially blocked one by one location. The slide shows the simple diagram. The origin point is where the block indicate starts. In mine like the Indonesia, planner set this origin carefully. It defines the reference of all the IJK block coordinates. For example, if the origin is lower left corner of the pit at the elevation of 2000 meter, then the block 111 is at this coordinate, those coordinate. All other blocks are built for that reference, like that. How does the Whittle differ from the Surpac? First, the Whittle uses the IJK identifications, numbers of the blocks in each direction. Instead of actual coordinates, it also stores the contain the metal like MCAF and PCAF instead of the grade. In Surpac, each block might say the gold is 2.5 gram per ton. In Whittle, we say the 4,500 pounds contains. Another difference, Surpac support the sub-blocking blocks, breaking the block into the pieces, where the Whittle uses the parcel part of the block. Also, the MCAF and PCAF and the slopes info attached to the block in the Whittle, while the rock and the grade go on the parcel. In short, the Surpac is the real coordinates plus the grades, and the Whittle is the index coordinate plus the metal. For example, when you export from the Surpac to the Whittle for the nickel mines, ensure you convert the grade to the metal properly. So Whittle has the accurate metal in each block, right? A parcel in the Whittle is the portion of the block for which we know the rock type, tonnage, and the contained metal. Think of one block as the possibly having the different material. One part could be ore, another part could be a waste. Each part is the parcel. The sum of all parcels in the block may equal or be the less than the block's total tonnage. Any leftover is undefined as the waste. For instance, if a block is 100 tons and the parcel total 80 tons of the known ore type, the other 20 is just the waste, right? If no parcels exist, the whole block is treated as the waste. Unlike Surpac sub-block blocks, parcels has no defined shape or the exact position. They are just the conceptual part of the block. In practice, at the coal block with the bit of seam and the mostly waste, people could show one parcel of the block and indicate the rest of the waste, right? The slide diagram of the block into the parcels A, B, and C1 to C3, each with its own ore type and tonnage. The calculation shows the profit by sum of all the parcels, multiply the cost, subtract the price. The key point is each parcel is evaluated separately for deciding where it goes, right? This means in one block, parcel A might go to the mill as ore, while the parcel B goes to the waste. The example table shows the metal and the tonnage for the parcels A, B, C. Another takeaway is that smaller parcel size allows the finer selectivities. For example, if the copper mine block has the both high grade core and the low grade cell, treating them as the separate parcel ensures the core goes to the ore and the shell goes to the waste, optimizing recovery, we can say this. Continuing from the diagram, since each parcel can go to the different designation in the mining can be selective even within one block. In our example, parcel A and B, light and blue section could be ore, while the C parcel might be waste, even if they are in the same block. This is the powerful for the mine planning. It likes having the very small sub block precision. Just remember, unlike the Surpac, Whittle doesn't know exactly where inside the block or each parcel, just the totals. But for scheduling, this is usually the enough. Overall, the parcel helps them maximize the profit by processing only the best material and avoiding the waste. To recap this session, Whittle uses the IJK coordinates, not the northeastern and the elevation. It just stores the content in metal like the pounds and rather than SA grades. Whittle blocks and the parcel functions similarly to the Surpac block and the sub blocks, but the parcel location and the shape are not tracked. Also, some block tonnage might be undefined,
like
waste
forms and rather than SA grids. Whittle blocks and the parcel functions similarly to the Surpac block and the subblocks, but the parcel location and the shape are not tracked. Also, some block tonnage might be undefined, waste if the parcel doesn't fill it. Importantly, each parcel can be mined or to the different designation on the, we can say, the ore and the waste. The selectivity can greatly affect the schedule and the revenue. Understanding those different keys when the converting the geological model like in the Surpac into the scheduling modeling in the Whittle or in the MineOpt. Easiest in the MineOpt, right? Datamine is another industry standard format for the block modules. Datamine block module files have the .dm extension. Thing to know: Datamine limits the field name to 8 characters and only 256 fields if using the extended precision format. So if your model has the dozens of the attributes, you may have to combine or split them. For example, a gold mine using the Datamine might name a field like the gold lowercase g, or we can say the ore type. Yeah, each only a 8 character. Remember that these constraints are important if you are exporting or importing the Datamine modules. Datamine block module comes in the two precision modules, the single SP and the extended EP. The original SP files were stored in the 2048 bits pages. The page 1 defines the total schema and the subsequent pages had the records. In similar terms, the first block of the data explains what each field is, then the rest of the file listed the block. Datamine also has the text alpha and the numeric data types. Internally, numeric data used with real 4 in the SP and the real 8 in the EP. For instance, coal mine seam thickness might be stored in the real 4 numbers in the Datamine module. Some specifics like the Datamine uses the A for the text field and the N for the floating numeric fields. It also has the special numeric codes as you can see in the screen, representing no data bottom like that. These conventions are important to recognize when reading the raw Datamine file or converting into the other format. This to be known in very careful. In summary, remember Datamine SP and EP are quite different under the hood. If you ever need to work with these, you might have to be export them into the different format for to likes the MineOpt, but often planner will export the Datamine to the CSV or the Whittle format anyway. The technical details here mainly ensure you to handle the data correctly. In practice, the companies like the Datamine, like some South African and the Russian operations, known to be check their precision method and field names when moving data between the systems, right? And finally, now let's look at the Minex, which is the specialized for the stratified deposit, think like the coal and the bauxite. Minex uses the grid model either than block module. The slide simply title the Minex model format. The details will come in the next slide. Minex grid model capture the seam geometry we can say. For example, an Australian coal mine might use the Minex to create the grids for the floor and the roof surface of each coal seam. Next, we will review how the Minex represent the geology as the triangles and the grids. Minex uses the combination of the triangular networks and the grids. First, we form the triangles by connecting the data points like the boreholes points and the survey points. This triangular mesh represent the surface constant seam roof surface in the coal deposit. Then the Minex computes the grid, the regular mesh of the point at the centroid of these triangles. So each grid needs the whole information like the XYZ that might represent the seam thickness and the topography, quality and the other attributes. For example, the Z value of the thickness of the grid is denotes the seam thickness at that location. This method ensures the smooth geological surface for the stratified layers. Minex grid file .grid as a representation of the grid file, just the mesh of the points. When you view it, you can see it as the network of the square if draw lines or the contours. The key is that each grid needs often at the square centers carries the value like the elevation and the thickness. For instance, the coal seam, as you can see in the floor, elevation.grd might store the floor elevation at each. So that plotting the grid gives you the continuous floor surface. In Minex, you can display the grid as the colored contour or the solid surface. It's very visualized. Yeah. Each grid file holds one attribute. You could have one grid for the seam thickness, or another seam for the seam floor, and another for the roof, and much more. This grid reside in the grid folders. We will see that in the next slide. Grids are named simultaneously, we can say, often like the seam name plus the suffix. For example, the seam name seam1 is like the floor for the seam1 thickness, and the seam1 is for the floor elevation, like that. In quality models, the z value could be stored something like the ash percentage or the calorific value instead of the elevation. So the Minex grids are very flexible, and one can model any charging attributes in the xy space. A grid needs to be in the grid folder .grt to be used in the Minex. Think of the folder as the collection of the grid from one project or the dataset. For example, on the slide mentioned in the ashes dataset with the folders like the blast.grid or the model.grid, the structure.grid. Each of these grid folders contains the multiple grid files, maybe the floor, roofs, and the qualities. For example, the model.grid might contain the seam surface for the geological model, while the blast.grid has the blast elevation surface. While exporting to MineOpt, you do export all the relevant grids from the these folders. You have to remember this. There are two main types of the grid in the Minex. Geological grids represent the solid boundaries, for example, the seam, floors, and the roofs. Quality grids represent the things like the ash content and the sulfur that varies across the deposit. When you open a geological grid in the Minex, it looks like the sheet continuous surface. In the example on the slide, topographic grid shows the 3 seam floor grid beneath it for the different layers. In practice, you might have the grid name to be topography for the surface, and the grid seam 1 floor and the seam 2 floor, and many more. Each one is the solid sheet representing that horizon, right? Stratified deposits are often weathered near the surface. For example, the top layer might be a oxide, or the accredited geologist typically model the base of the weathering surface from the data like the holes. In the Minex, there are the special grid for these, above which no economical seam exists. This means many blocks or the areas above the base of the, we can say, the weathering grid are non or weathered west. For example, at the coal mine in India, if you base of the weathering grid is 100 meter, nothing above the 100 meter is coal, right? This grid helps stream the model, so we don't plan the mining above that level. The borehole database in the Minex stored all the drill hole sample data. Practically, this means the collar position, downhole survey, and the SA values. Minex displays this as the .b31 file. Behind the scenes, there are the 5 files, but you only see the b31 in this interface. For example, at the mine site, every drill hole with the coal seam feeds into this dataset. You can just query the depth of this coal and the correlated logs, or generate the grids for it. For our purpose, just know that .b31 is the link of all your drilling info in the module. Coal seam stack in this strategic order, the oldest first. Yeah, Minex keeps to track this sequence in the .b31 file. This file lists each seam in the order and its property like the default density for every hole. These are two types, the B35 and the B35S. In practice, mining engineer will use this to ensure the model to know which seam is above in each borehole. For example, in the coal mine in the Queensland might have the seam ABC in each hole, and the B35 file ensure that they line up correctly. If you open the B35 file, you do see the columns for seam ID, thickness, and the density. Datamine Minescape is another format for the stratified deposit. Here we wasn't detailed every Minescape steps, but keeping in mind, Minescape also produce the grid and the table for the seam models. It often used the major by the major coal companies. For the Minescape, data must be exported properly. The key is the after modeling in the Minescape. We will export the serial files for the MineOpt, right? That covers all the slide for the block module type and data prep. In the next video, we will move in on the scheduling and how these modules fit into the long-term plans. Thanks for watching. Here is Prakal signing off. Thank you so much.